Okay, so hello everyone. So do click do in the live chat say hi to madam. So we shall start our class tonight. So tonight I will go through haloalkane. So I will start on haloalkane. So some classes already started the haloalkane, but I only went through the eliminations and also insertion to form Grignard reagent. So I haven't started the introductions of haloalkanes and also the nucleophilic substitutions reaction. So tonight, basically, we will go through the introductions of haloalkanes and also to discuss about the nucleophilic substitutions reaction. So the nucleophilic substitutions reaction is very, very important. So every year, at least one question regarding on the nucleophilic substitutions of haloalkane. So do need to pay attention on the reactions mechanism. So now shall we start? So for haloalkane, basically we have the halogen functional group attached to sp3 hybridized carbon atom. So in haloalkane, we have carbon, okay, so the halogen, attached to sp3 hybridized carbon atom. So haloalkane, the functional group is halogen. So it can be fluorine, chlorine, bromine, iodine. And the general formula for haloalkane, basically for acyclic haloalkane, means that straight chain, not ring. The general formula is CnH2n plus 1x. If it is cyclic haloalkane, so the general formula is CnH2n minus 1x. Okay, where your X can be fluorine, chlorine, bromine, or iodine. So you need to know how to class your haloalkane. So this is very, very important. Okay, because in the SN1, SN2 reaction, if you do not know how to class your haloalkane, then you can't do. Okay, so we shall have a look on how to class the haloalkane. So first, we need to circle the reference carbon. So where is the reference carbon? The carbon that attached to the halogen group. So this is the reference carbon. So if the carbon attached to the halogen has all hydrogen around it, so 3 hydrogen around it, then we have methyl halide. Okay, we have methyl halide. So if the carbon attached to the halogen has 2 hydrogen, means that has 1 alkyl group. So if having 1 alkyl group, means that it is a primary haloalkane, or we can call it as primary halide, or we call it as primary haloalkane. Both is acceptable. Okay, so and then the reference carbon is the carbon that bonded to a halogen. If only 1 hydrogen, means that 2 alkyl group. So if 2 alkyl group, means that it is a secondary halide or secondary haloalkane. Okay, then we move on to look at if the reference carbon that attached to the halogen has no hydrogen attached to it. So if no hydrogen attached to it, means that all are alkyl group. So having 3 alkyl group around it, then we have tertiary halide or tertiary haloalkane. So if we have halogen directly bonded to the benzene ring or the aromatic ring, then it is called aryl halide. Okay, aryl halide. For example, your bromobenzene is aryl halide. Okay, so however, look at this. This is not a real halide. Okay, so this is So where is your reference carbon? This is the carbon. So this carbon is the one that bonded to the halogen. So this carbon has 2 hydrogen around it. So means that has 1 alkyl group. Okay, so having 1 alkyl group, so it is actually primary haloalkane. Okay, it is primary haloalkane. It is because the halogen is not directly bonded to aromatic ring, so it is not a real halide. Okay, so now we move on to look at how to class the haloalkane. So again, first we circle the reference carbon. So if you can't see like this, you can expand it. So the carbon bonded to the hydrogen, another one to the bromine. On both sides, CH3, CH3. So where is the reference carbon? So this is the carbon because it is bonded to the halogen. So this carbon has 1 hydrogen. So if 1 hydrogen means that 2 alkyl group. So if 2 alkyl group, so it is secondary haloalkane. Okay, so now we'll move on to look at the next one. Circle the reference carbon. So this reference carbon is the one that bonded to the halogen. It has 2 hydrogen, means that 1 alkyl group. So if 1 alkyl group, this is primary haloalkane. 1 alkyl group attached to it, so primary haloalkane. So now we move on to look at this example. So this example, so if you can't see it this way, you can always expand it. So this carbon attached to CH3, CH3, so CH3 and the Cl. So circle your reference carbon. So this is the reference carbon, which is bonded to halogen. Can you see that no hydrogen attached to it? So means that having 3 alkyl group. So if having 3 alkyl group is tertiary haloalkane. So we move on to look at the next one. So this is the reference carbon because it is bonded to the halogen. Can you see that no hydrogen attached to it? So if no hydrogen attached to it, means that having 3 alkyl group. So if having 3 alkyl group, so means that it is tertiary haloalkane. So this is how we class the haloalkane. Again, very important. We are going to see this in SN1 and SN2 reactions mechanism again. So now we move on to look at how to name haloalkane. So if you remember the priority table in the benzene, so remember haloalkane is the lowest. So since it is the lowest, it will always be the substituent. Always be the substituent. Okay, so how do we name haloalkane? So basically, it's how we name alkane. So alkane, remember, first we need to find the longest continuous carbon chain, and then we number the carbon chain in a way that we measure the first substituent lowest possible number. Okay, so do the same thing for haloalkane. Okay, and then for the haloalkane, halogen, when it becomes the substituent, so if we have fluorine, it is fluoro, chlorine, chloro, bromine, bromo, and iodine, iodo. And then we need to name them according to the alphabetical order, okay, with other substituents. So now, shall we move on to look at how to name the haloalkane? So it's just like how you name your alkane. It's just like how you name your alkane. Find the longest continuous carbon chain first. So in the first compound here, where is your longest continuous carbon chain? So can you see? It's this. Okay, so it's this. So how should we number the parent chain? So measure first substituent lowest possible number. So it will be 1, 2, 3, 4, 5. So this parent is called pentane. And substituent we have 3-chloro and also 3-methyl. Remember, we need to name them in the alphabetical order. So C comes first. So the name of this compound, therefore, is 3-chloro, 3-methyl pentate. Okay, so now how about in the ring? So in the ring, so can you see that ring have 5 carbon? So this must be the parent. So must be the parent. So this parent is called cyclo 5-member ring. So cyclopentate. So what substituent do we have? So remember, this one have 3 substituents. So if we are having 3 substituents in the ring, make sure we number in a way that we get the lowest possible location for each of the substituents. So means that we need to start here number 1, number 2, number 3. So what substituent do we have? So we have 1 iodo, we have 1 methyl, and 3 ethyl. Again, alphabetical order. So E first, I, and then the M. So the name of this compound, therefore, will be 3-ethyl, 1-iodo, 1-methyl cyclopentane. Okay, so now we move on to look at so the next one. So the next one, okay. So shall we see where is the longest continuous carbon chain? So can you see here there's a carbon-carbon double bond. So carbon-carbon double bond must be the parent, higher priority. So this one should be the parent. So where we should start numbering the carbon on the parent chain. Again, now we have functional group, carbon-carbon double bond. So that is the priority, okay, because it has higher priority. So make sure the carbon-carbon double bond, lower possible number. So therefore, this must be 1, this is 2, this is 3, this is 4, this is 5. Okay, and this parent, we should call it as 2-pentene because carbon-carbon double bond is at carbon number 2 and number 3. Substituent, we have 4-bromo and 3-methyl. Therefore, this compound should be called 4-bromo, 3-methyl pentene. Okay, so another example. So the last example. So where is the longest continuous carbon chain? So this carbon chain, so shall we see? Okay, so this is the longest continuous carbon chain. Consists of how many carbon? So measure the first substituent, lower possible number. So it's 1, 2, 3, 4, 5, 6. So the parent is hexane. Substituent, we have 2,3-dimethyl. And another one on your third carbon. So this is the substituent. So how do we put the substituent? Can you see that in this substituent, inside this substituent, we have another substituent which is chlorine. Okay, so which is chlorine. So when we have the substituent, where inside the substituent you have another substituent, dalam substituent, how do we write it? So we need to write the position at the parent chain. It is number 3. So inside this carbon number 3, this substituent, we have another substituent. So because of that, we need to bracket it. We need to bracket it because inside this substituent, kita ada satu lagi substituent, which is the chlorine. So because of that, we need to put a bracket. So this is chloromethyl. Okay, chloromethyl. So when we name it, which one comes first? So this is C and this is M. So therefore, it is called 3-chloromethyl. Okay, I write that side a bit because it's quite a long name. So name will be 3-chloromethyl. Two, 3-dimethyl hexane. Okay, so again, if you have substituent inside the substituent, you need to bracket it. Okay, so you need to bracket it. Okay, so to tell people that there's a substituent dalam substituent. So, okay, so another two compound. So shall we have a look? So this should be the parent. So this parent is, okay, shall we number first? So here's two substituents, 1, 2, 3. So the parent is pentane, cyclopentane. Okay, so cyclopentane. Okay, so substituent, we have 1 methyl, we have 1 ethyl, and also this is 3. Can you see that we have substituent? So this is a substituent. So we have substituent within the substituent, and this substituent is attached to carbon number 1 of the substituent, and this is carbon number 2. So therefore, we need to put the position 1-chloro ethyl. Okay, and then arrange them in the alphabetical order. So this is C, this is E, and this is M. So which one comes first? So of course it's C. So 3, 1-chloro ethyl, 1 ethyl, 1 methyl. Not enough space. Okay, so cyclopentane. So not enough space, so I write the whole name. So the last compound, you do it as homework. Okay, so name it yourself. So after done with the IUPAC nomenclature, then now we move on to look at the structure of haloalkane. So basically, haloalkane, okay, in haloalkane, just now I already told you that in haloalkane, the halogen is attached to the sp3 hybridized carbon. So this sp3 hybridized carbon, okay, is having the tetrahedral geometry. Okay, so let me draw in the tetrahedral. So still remember the tetrahedral geometry. So means that you are having the tetrahedral shape. Okay, so the tetrahedral shape. That is what meant by the halogen in the haloalkane attached to the sp3 hybridized carbon. And then the carbon halogen bond, so means that this bond is a polar bond. Why is it a polar bond? Because halogen atom is more electronegative than carbon. So because of that, this bond is a polar bond. Okay, and then the intermolecular forces present between the haloalkane molecule, therefore will be the dipole-dipole forces and also the London dispersion forces, because haloalkane is a polar molecule due to this bond being polar. Okay, So, and then since this bond is polar and halogen being more electronegative, therefore halogen will be partially negatively charged, and the carbon of the haloalkane, which is bonded to halogen, is partially positive charged. And because this carbon is partially positive charged, means that it is poor in electron, misking electron, and it is susceptible, means that cenderung, being attacked by the nucleophile. So nucleophile will attack this carbon. Okay, so later on you will see the nucleophile will actually attack from the back in the SN2 reactions mechanism. Okay, to replace the halogen. Okay, so because of that, the type of reaction your haloalkane can undergo is nucleophilic, because this carbon partially positively charged, so cenderung attacked by the nucleophile. That's why it's nucleophilic. Okay, when it is being attacked by the nucleophile, what will happen is this halogen will be replaced. Okay, that's why the reaction, the type of reaction haloalkane can undergo is nucleophilic substitution reaction. So for haloalkane, so haloalkane can undergo 3 types of reaction. Okay, so the one that we are going to discuss tonight is nucleophilic substitutions reaction. Okay, whereby the nucleophile attack the partially positively charged carbon atom that is bonded to halogen and then replace the halogen. Okay, so this is the general reaction for nucleophilic substitution, where nucleophile attack the carbon that is partially positive charge, tendang keluar the halogen, so replace the halogen. Okay, so the halogen will come out as the leaving group. Okay, and another 2 reaction haloalkane can undergo is elimination. You have seen in the alkene chapters, and another one is insertion. So 2 classes have seen this. Okay, for 146 and 234, don't worry, we're going to look at this tomorrow. So tonight we just focus on nucleophilic substitutions reaction. Okay, so now we move on to look at the first nucleophilic substitutions reaction. Okay, so if your haloalkane react with NaOH, NaOH is ionic compound. So it's ionic compound, sodium ion and also the hydroxide ion. Which one is your nucleophile? Remember, nucleophile. So nucleophile is electron rich. So in your sodium hydroxide, which one is your nucleophile? It's just the the hydroxide ion. So this is your nucleophile. This is your nucleophile. Therefore, only the hydroxide ion will attack the carbon that is partially positive charged in your haloalkane to replace the halogen. Okay, so to give you the byproduct sodium halide. Okay, so for example, so this haloalkane react with sodium hydroxide. So first, you must know sodium hydroxide is ionic compound. Which part of the ionic compound that is the nucleophile? Is the hydroxide ion. Therefore, and then in your haloalkane, where is the carbon that is partially positive charged? Is the one that attached to the halogen. So the nucleophile will come in, attack this carbon, tendang keluar the halogen. Okay, and the product that you get will be this, the alcohol. Okay, so since this is the equation, so the byproduct or the side product, so the bromine come out as the bromide ion, so we'll give you sodium bromide. That is the byproduct. But again, when we talk about product, this is the product. Okay, so now we move on to look at reactions with hydroxide. So your haloalkane react with hydroxide. So beside coming from the sodium hydroxide, it can also come from water. Oh, another thing before I forget. Okay, so you need to be careful. If sodium hydroxide aqueous, then it will undergo nucleophilic substitutions reaction with haloalkane. If aqueous, will undergo nucleophilic substitutions reaction with haloalkane. But if sodium hydroxide in ethanol and reflux, this is not nucleophilic substitution. Okay, so not nucleophilic substitution. This is for elimination. Remember, in elimination of haloalkane, we need base. So the base can be sodium hydroxide, but the solvent will be ethanol. Okay, so in order for nucleophilic substitution to occur when we use sodium hydroxide, it needs to be aqueous. Means that the solvent must be water. The solvent must be water. Okay. So now we move on to look at, so besides using sodium hydroxide, which can give us hydroxide ion as the nucleophile, we can also use water. We can also use water to give us hydroxide ion. Okay, so basically, the carbon that is bonded to the halogen is partially positive charge. And we know that in water, so I will draw out water like this. So in water, the oxygen is partially negatively charged and it has 2 lone pair. Okay, so what happened during the nucleophilic substitutions reaction is the oxygen of the water use the lone pair to form bond with the carbon that is partially positive charge, and then tendang keluar the halogen, and the halogen keluar will take one of the hydrogen. That's why the byproduct is HX, and your product is the alcohol. Okay, so again, the carbon that is bonded to halogen is partially positive charge, and the water on the oxygen has the lone pair. It is partially negatively charged. So what is happening is, during the nucleophilic substitutions reaction, oxygen using the lone pair attack the carbon that is partially positive charge, tendang keluar the Br. And the Br keluar ambil one of the hydrogen. Okay, so therefore your product is alcohol. Your product, so can you see the oxygen is attached to this carbon? Oxygen attached to this carbon, and this oxygen ikut dia masih ada hydrogen ini. So you get the alcohol, and the byproduct is HBr. So for haloalkane to react with the hydroxide ion or water, so you just need to know, for the hydroxide ion, it is a strong nucleophile. Hydroxide ion, because negatively charged, it is strong nucleophile. Water only having the lone pair, so it is weak nucleophile. Okay, so you must remember this. Hydroxide ion, strong nucleophile, water, weak nucleophile. So then we move on to look at, so beside hydroxide ion, we can also have alkoxide ion, which act as the nucleophile. So in sodium alkoxide, so again, sodium alkoxide, this is ionic compound. So sodium ion and also the alkoxide ion. So which one is your nucleophile? Is this alkoxide ion is the nucleophile? Not the whole sodium alkoxide. Okay, it's just the alkoxide ion is the nucleophile. So again, what is happening is the carbon that is bonded to halogen is partially positively charged. So alkoxide ion, okay, will attack the carbon that is partially positive charge, tendang keluar the halogen. So tendang keluar the halogen to give you ether, okay, to give you ether, okay, and the byproduct sodium halide. Okay, so for example, so shall we look at this example? So this carbon is partially positive charge. It's about bonded to halogen. Right? And then, so this is your sodium alkoxide. So in your sodium alkoxide, this is ionic compound. Which one is the nucleophile? So here we have sodium ion and also the alkoxide ion. The alkoxide ion. So this alkoxide ion is the nucleophile. So this nucleophile at the oxygen will attack the carbon that is partially positive charge and tendang keluar the chlorine. Tendang keluar the chlorine. So can you see that this oxygen will be attached to this carbon, will be attached to this carbon. So therefore, you will get CH3, CH2, and then sambung ke oxygen ini. And together, belakang dia CH2, CH3. So you get the ether as your product. And the byproduct, so yang ini chloride ion keluar will pair with sodium ion to give you sodium chloride. So beside the alkoxide ion coming from sodium alkoxide, it can also come from alcohol. It can also come from alcohol. Okay, so for example, so again, this is the carbon attached to the halogen. It is partially positive charge. Okay, and in the alcohol, the oxygen have two lone pair. Okay, so the oxygen of the alcohol will use the lone pair to form the bond with the carbon, and then tendang keluar the halogen, and the halogen keluar, so it can the halogen, it will take hydrogen. Dia akan ambil hydrogen. You won't take this. Kenapa? Okay, so again, halogen kecil. So easier for the halogen to take the hydrogen compared to the alkyl group. So because of that, your product will be the ether and the byproduct HX. So sekali lagi, so in the example, can you see that this carbon is partially positive charge because it is bonded to the halogen. Okay, and in the alcohol, it has two lone pair on the oxygen. So the oxygen will use the lone pair to attack the carbon. Tendang keluar the Br. So means that this carbon is bonded to the oxygen, and the Br keluar will take the hydrogen. Okay, so what will be your product? So again, this carbon attacked by the oxygen. So therefore, akan sambung to the oxygen. And then this oxygen is attached to CH2, CH3. So CH2 dulu. So you write CH2, then only CH3. So this is your ether. And the byproduct will be HBr. Okay. So now we move on. Oh, before that, again, need to remember. So alkoxide ion, if it is from the sodium alkoxide, you can see that is negatively charged. So it is strong nucleophile. If it is from the alcohol, the H is still attached to it. So this is weak nucleophile. From alcohol, weak nucleophile. From sodium alkoxide, strong nucleophile. So then now we move on to look at, So nucleophilic substitution on haloalkane can also occur by using carboxylate ion. Okay, so this is carboxylate ion. So if you draw it out, basically it is like this. C double bond O, O minus. So this is carboxylate ion. Carboxylate ion is just moderate nucleophile, means that not too strong, not too weak. Okay, so again, where can we get the carboxylate ion? From sodium carboxylate. Okay, from sodium carboxylate. Again, in sodium carboxylate, where is the nucleophile? It's only the carboxylate ion is the nucleophile. Sodium ion bukan nucleophile. Remember, nucleophile refer to the electron-rich species. Electron-rich species. So this carboxylate ion rich in electron at the oxygen that carry the negative charge. Therefore, the oxygen which carry the negative charge will attack the carbon in the haloalkane, which is partially positive charge. And then tendang keluar the halogen. Okay, so what you will get is, so basically your R come here. The halogen already come out. Okay, combined with the sodium ion to give you sodium halide. Okay, so again, in your sodium carboxylate, your nucleophile is CH3COO minus. So if you can't see, you can expand it, COO minus. Okay, and it will attack the carbon that is partially positive charge. So this carbon, because it is bonded to halogen. So basically, it will come in, attack this carbon, tendang keluar the halogen. So tendang keluar the halogen. Okay, so you will get CH3, CH2, and then bonded to this carbon is this oxygen. So you can draw to the oxygen. Okay, and then only this carbon, C double bond O, another side CH3. You can draw like this. Okay, so you get your ester. And then the byproduct will be sodium chloride. Okay, so this is nucleophilic substitution reactions on haloalkane using carboxylate ion. So now we move on to look at for nucleophilic substitutions reaction on haloalkane. You can also use cyanide ion. Cyanide ion. For cyanide ion, it is a strong nucleophile. It is a strong nucleophile. Okay, so negative, it is small and negatively charged. So it is a strong nucleophile. So in your example, in your potassium cyanide, so where is the nucleophile? It is a cyanide ion. It is the cyanide ion. So the negative charge is actually on the carbon. It is on the carbon. And this carbon that is bonded to halogen is partially positively charged. Therefore, it will be attacked by the cyanide ion, tendang keluar the halogen. So you get your compound. Okay, so and then so this is your nitrile compound, and your byproduct so will come out as the X minus combined with the potassium ion to give you potassium halide. Okay, so again we look at the example. So for potassium cyanide, where is your nucleophile? Your nucleophile is the cyanide ion, and the negative charge is on the carbon. So, and this is the carbon in your haloalkane that is partially positive charge. So the cyanide ion will attack the carbon that is partially positive charge, tendang keluar the halogen. So after tendang keluar, so what you will get is, so this carbon will be bonded to the carbon of the cyanide ion. Okay, so CH2, and then bonded to CN. That is your nitrile compound. And then your byproduct will be KCl. Okay, so now we move on to look at the next one. So your cyanide ion, okay, so this carbon is partially positive charge. So for cyanide ion, remember the negative charge is on the carbon, And this cyanide ion, strong nucleophile attack the carbon that is partially positive charge, tendang keluar the Cl. So you will get CH3, CH, so CH3, CH, Cn, CH3. And then Cl minus as the leading group. Okay, so again, this carbon is attached to carbon of the nitrile group because, again, the negative charge is on the carbon. Then now we move on to look at nucleophilic substitutions on haloalkane using excess ammonia. So if using excess ammonia, so ammonia, you see there's no negative charge, so it is weak nucleophile. It is a weak nucleophile. It is nucleophile because dia kaya electron. Dekat mana? On the nitrogen. It has one lone pair. That's why it is rich in electron. So for ammonia, rich in electron because lone pair on the nitrogen. The carbon that attached to the halogen is partially positive charged. Okay, so the nitrogen using the lone pair attack the carbon, tendang keluar the halogen. And the halogen keluar, so we'll take one of the hydrogen. We'll take one of the hydrogen to give you the byproduct HX. And you get R, basically this is amine. You get amine. So example, again, okay, I always explain like this. So this carbon attached to halogen, it is partially positive charge. So will be attacked by the nitrogen using the lone pair. Tendang keluar the halogen. Halogen keluar akan ambil the hydrogen. So the product that you get will be NH2 and the byproduct is HBr. Okay, so the next example, also the same thing. The carbon that attached to Br is partially positive charge. Okay, so the nitrogen or ammonia is rich in electron. Use the lone pair attack the carbon, tendang keluar the Br. Br keluar, ambil the hydrogen. So what you get? You get your amine. And the byproduct, HBr. Okay, so the important thing is you'll be able to draw the product. So how to conclude this? Okay, so what conclusions can we make? So if you have neutral nucleophile, for example, water, okay, alcohol, and also ammonia. So what will happen is when the halogen keluar, they will take the hydrogen, will take one hydrogen. Okay, if you have an ion such as hydroxide ion, alkoxide ion, or carboxylate ion, or cyanide ion. So what will happen is, when the nucleophile that is negatively charged attack the carbon, tendang keluar the halogen akan keluar as the anion, So will not take the hydrogen. So that is what I want to conclude. Okay, and then you need to know those with negative charge, they are strong nucleophile. For example, hydroxide ion, alkoxide ion. Okay, so only your carboxylate is the moderate nucleophile. Your cyanide ion, so they are negatively charged, so they are strong nucleophile. Okay, so those are neutral with lone pair, such as water, alcohol, and also ammonia. They are weak nucleophile. Okay, so neutral with lone pair, they are weak nucleophile. If negatively charged, they are strong nucleophile. Okay, so with that in mind, then now we can move on to look at nucleophilic substitutions reaction mechanism for haloalkane. So for haloalkane, when it undergo nucleophilic substitutions reaction, boleh melalui dua different mechanism. Okay, so the first one is SN1. So one bermaksud, one here means that at the slower step or rate determining step only involve one molecule. That's why called SN1, unimolecular nucleophilic substitutions reaction. Okay, so means that at the slower step hanya melibatkan satu molecule. Remember just now, haloalkane need to react with nucleophile in order for the substitutions reactions to occur. If in SN1, okay, basically at the slower step of the reaction, hanya melibatkan haloalkane. Okay, so the slower step of the reaction hanya melibatkan haloalkane. Okay, so the slower step of the reactions mechanism, or we say rate determining step, only involve haloalkane. Therefore, it is being called as SN1. The reactions mechanism dipanggil SN1 because at the slower step of the reaction hanya melibatkan haloalkane, hanya melibatkan the haloalkane. Therefore, if we want to write the red law of the SN1 reaction, we only write rate equal to rate constant multiplied by the concentrations of haloalkane. Sebab in the slower state, only melibatkan haloalkane. So only the concentrations of haloalkane can affect the rate of the reaction. Okay, so for SN1 reactions to occur, basically it involves weak nucleophile. It involves weak nucleophile. Remember, what is the weak nucleophile? Example of weak nucleophile: alcohol, your water, your ammonia. So these are weak nucleophile. Okay, so usually weak nucleophile, okay, will be related to SN1. And for SN1 reaction, it will form carbocation intermediate. So this is very important. You must remember, for SN1 reaction mechanism, it will form carbocation. And for SN1 reaction, it usually occur in two steps. Okay, occur in two steps. And then the reactivity towards SN1 basically decrease from tertiary haloalkane to methyl halide. Kenapa? Because tertiary haloalkane, remember in SN1 melibatkan pembentukan cation, carbocation. So tertiary haloalkane can give tertiary carbocation, which is the most stable. That's why tertiary haloalkane most reactive towards SN1. Sebab tertiary haloalkane can form tertiary carbocation. While for methyl halide, so methyl halide, it will form methyl cation, not stable at all. That's why the least reactive towards SN1. So in SN1 reactions mechanism, steric effect is not important. So later on I will explain what is steric effect. So that is SN1. So in the slower step hanya melibatkan satu molekul iaitu haloalkane. That's why it is being called as unimolecular nucleophilic substitution. Sebab slower step melibatkan satu molekul sahaja iaitu haloalkane. So now we move on to look at SN2. So 2 means that at the slower step or rate determining step involve both haloalkane and also the nucleophile. Involve both haloalkane and also the nucleophile. Therefore, for SN2 reaction, it is being called as bimolecular nucleophilic substitution. So bi bermaksud dua. In the rate determining step, melibatkan dua benda, dua pihak, iaitu the haloalkane and also the nucleophile. Therefore, when we write the rate law for SN2 reaction, we write it as rate equal to rate constant multiplied by the concentrations of haloalkane multiplied by the concentrations of nucleophile, because both nucleophile and also the haloalkane are going to affect the reactions rate in the SN2 reaction. It is overall second order reaction, but for for SN1, overall is a first order reaction because only affected by haloalkane. Okay, so for SN2 reaction, it requires strong nucleophile. Still remember what is strong nucleophile? Example, it must have the negative charge. So cyanide ion, hydroxide ion, and your alkoxide ion. So those with the negative charge. Okay, so and then for SN2 reaction, it will form activated complex at the transition state. So later on, we are going to see how to draw this. And then for SN2, basically it involves one-step mechanism. So basically for SN2, one step bermaksud like this. So here is your haloalkane and also nucleophile. So when they react, they form the transition state and then the product. So this is one step. Okay, but for SN1 will be two steps, whereby, okay, so step number 1, you have your haloalkane. Okay, it will form the carboxyl ion, and then here the carboxyl ion will react with the nucleophile, then only give you the product. So can you see two steps? Okay, that is what it meant. For SN2, the reactivity decreased from methyl halide. Okay, so methyl halide most reactive. Okay, so decrease from methyl halide to tertiary haloalkane. Okay, so I will explain in details later on why. Because in SN2, steric effect is important. So larger steric effect means that less likely to undergo SN2. Okay, we are going to look at this in detail later on. So how to choose whether that particular haloalkane is going to undergo SN1 or SN2? So remember, SN1 will form carboxyl ion intermediate. So which class of haloalkane will give the most stable carboxyl ion intermediate? So it's tertiary haloalkane. Therefore, tertiary haloalkane will definitely undergo a nucleophilic substitutions reaction through SN1 reaction mechanism. Okay, and for methyl halide, So methyl halide, remember, O are hydrogen around it. So O are hydrogen around it. So means that nucleophile easy to get the carbon. So easy to get the carbon that is bonded to the halogen. So if easy to get, then it is more likely to undergo SN2. Okay, more likely to undergo SN2. So methyl, if you see methyl halide, definitely SN2. If you see tertiary haloalkane, definitely SN1. Then how about primary haloalkane? So if primary haloalkane steric effect is not much steric effect, it will proceed through SN2 reaction mechanism. So if high steric effect, then it will proceed through SN1 by forming the carbocation. It will undergo rearrangement to form stable carbocation, okay, through SN1 reaction mechanism. So for secondary haloalkane, we need to look at the nucleophile. That's why I told you nucleophile very important. So weak nucleophile, remember SN1 can accept weak nucleophile. Therefore, if we are having weak nucleophiles such as water, okay, so alcohol, okay, or ammonia, then secondary haloalkane will proceed through SN1. So if we are using strong nucleophile, such as hydroxide ion, alkoxide ion, cyanide ion, then the secondary haloalkane will proceed through SN2 reactions mechanism. So now we look at the mechanism in details. So again, SN1, so unimolecular nucleophilic substitutions reaction. So I told you already, means that at the slower step or rate determining step, only involve haloalkane. Satu sahaja. That's why it is uni bermaksud at the rate determining step, satu species sahaja involved. That is your haloalkane. Okay, involved in the reaction. So basically, unimolecular nucleophilic substitutions reaction SN1 involve two steps, and it will involve formations of carbocation intermediate. Okay, so I told you already, tertiary haloalkane definitely will undergo SN1 because tertiary haloalkane give most stable tertiary carbocation. Therefore, if you see tertiary haloalkane, definitely it will proceed nucleophilic substitutions reaction through SN1 reaction mechanism. Okay, so for SN1 reactions mechanism, the reactivity of haloalkane for SN1 reactions mechanism is determined by the stability of carbocation. So for tertiary haloalkane, give most stable tertiary carbocation. So therefore, tertiary haloalkane most reactive towards SN1. Okay, sebab tertiary haloalkane boleh menghasilkan tertiary carbocation which is the most stable. Therefore, it is most reactive towards SN1. Okay, so and then the reactivity decrease from tertiary haloalkane to the methyl halide because the stability of cation decreases from tertiary carbocation to secondary, primary to methyl carbocation. So now, shall we move on to look at the reactions mechanism? So before we look at the reactions mechanism, step number 1, we need to look at our haloalkane. So this haloalkane, what class is this haloalkane? So this haloalkane, the reference carbon attached to no hydrogen. So if no hydrogen means that 3-alkyl group. So if 3-alkyl group means that this is tertiary haloalkane. So if tertiary haloalkane means that the mechanism that this nucleophilic substitutions reaction is going to follow through is SN1 reaction mechanism. So means that this haloalkane will react with the nucleophile, it is going to proceed through SN1 reactions mechanism. Okay, so before we move on, shall we look at the product first? So I already told you what happened. The carbon that bonded to the halogen is partially positive charge. And the nucleophile is water. So water, the lone pair, the oxygen has the lone pair, can use the lone pair attack the carbon, tendang keluar the Br. So Br keluar akan ambil one of the H of the water. We'll take one of the H. So give you the product. So you see, it's the oxygen that attack the carbon. So it will be bonded to oxygen and the H. And the Br keluar ambil one of the hydrogen. So the HBr will be the byproduct. Okay. So I told you already, this is tertiary haloalkane. The mechanism that it is going to go through is SN1. It is going to go through SN1 reaction mechanism. So how to draw SN1 reactions mechanism? So remember, SN1. So means that only involve haloalkane. So the step number 1 only involve haloalkane, only involve this, the haloalkane. Only one means that involve one species at the rate determining step. So that is the haloalkane. That's why step number 1, you only need to draw the haloalkane first. Okay? So, and then in step number 1, how to form the carboxyl ion. How to form the carboxyl ion. So basically involve bond breaking. So which bond need to break in order to give you carboxyl ion? So this bond. Okay, so this polar bond need to break. So after bond breaking, the 2 electrons will go to bromine. Why? Because bromine more electron negative. So what you get is, so tengok carbon ini. So this carbon only have 3 covalent bond. Remember, carbon 4 valence electron, -3, so +1. Okay, and then Br will leave as Br minus. So this step number 1, okay, is the rate determining step. Remember, just now I told you already, rate determining step is the slowest step in the reaction. And then this rate determining step only involve satu species sahaja, yaitu haloalkane. That's why it is SN1. Okay, SN1. So after step number 1, we get the carboxyl ion. Okay, so this is tertiary carboxyl ion, which is very stable. And now we move on to look at step number 2. So step number 2, so just now step number 1, we get the carboxyl ion. So step number 2, the nucleophilic attack on the carboxyl ion. So our nucleophile is water. Okay, so water will use the lone pair to attack the carbon. So two electron, okay, wait. So two electron form a bond with the carbon. So giving you, so two electron ini membentuk satu bond with the oxygen. Now look at the oxygen. Oxygen 6 valence electron, but now 1, 2, 3, 4, 5. So here positive charge. Okay, so this is step number 2, and this is very fast, relatively faster than the step 1. Okay, then after step number 2, we still haven't got the product yet, right? Our product is just OH, the alcohol. So means that another hydrogen need to come out. Okay, another hydrogen need to come out. So in step number 3, basically involve loss of proton. Means that you want to remove the hydrogen ion. Okay, so how? So after step number 2, you get this. So in step number 3, you bawa ni turun je. You bring it down. So who can come in to remove the hydrogen? Who can come in to remove the hydrogen? So basically is the water. Okay, because there are plenty of water in the reaction. So it will come in. So remember, you want to get your product, this bond must break. So when the bond break, it need to go to oxygen. Sebab oxygen lebih electronegative. Okay, and then someone need to take this hydrogen. So who will come in to take the hydrogen? So the lone pair of the oxygen. So you get this. You get your product and H3O plus. Okay, so basically this is the 3-step reaction for SN1 on the haloalkane, on tertiary haloalkane. So am I too fast? Am I too fast, class? Okay, so SN1, SN2 reactions mechanism, again, very important. Every year, definitely one mechanism will come out. So need to learn this properly. So then now we move on to look at SN2. So SN2 is bimolecular nucleophilic substitution. Means that at the slower step melibatkan kedua-dua haloalkane and also nucleophile. So means that in your first step itu, you need to draw both haloalkane and your nucleophile. Oh, before I forgot, the last step here, this one is also fast. Need to label it. So for SN2, okay, so in the slower step, again, bi or 2 means at the slower step, melibatkan haloalkane and also nucleophile. So you need to draw both, okay, haloalkane and nucleophile in your step number 1, okay. So basically, it involves only one step, okay. So, and then in the SN2 reaction, the nucleophile will attack from the back. So what does it mean? Okay, so basically it means that it will be attacking at the opposite side to the carbon that is bonded to the halogen. So basically it means like this. So this carbon Remember, it is tetrahedral shape. So having the tetrahedral shape. Okay, and it is bonded to halogen like this. Basically, nucleophile attack from the back means the nucleophile akan serang at the side that is opposite to the carbon that is bonded to the halogen. So, dari belakang. Okay, belakang of the carbon that is bonded to the halogen. Okay, opposite to the side where the carbon is bonded to the halogen. And then will form transition state. So transition state. So what does it mean? So transition state is the state di mana the carbon, when it is being attacked by the nucleophile, so it will partially form bond with the nucleophile. Okay, so partially, when we draw dot 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 like this, partially forming bond with the nucleophile, and then partially breaking the bond with the halogen. Okay, and remember last semester you learned, so ini ada 3 bond, 4, 5. So if 5, it will be a trigonal bipyramidal. So means that when you draw the transition state, because 5 bond, so you need to draw trigonal bipyramidal. So like this. Okay, so this is the transition state. Remember chapter 1, SN2, I told you already, the symbol is double dagger, okay, to represent transition state. And there is a negative charge sebab -1 sebab nucleophile -1, -1 neutral, so here -1. So this is a transition state di mana involve partial bond breaking, bond forming between nucleophile and the carbon, and partial bond breaking between the carbon and the halogen. Okay, and then because of the nucleophile serang at the opposite side, okay, opposite to the carbon bonded to halogen, so the product that form will have inversions of the configuration, has inverse configuration. So apa maksud inverse configuration? So bermaksud this tetrahedral at first pointing ke belah kiri. In the product, the tetrahedral will be pointing to belah kanan. Like this. Okay, this is what meant by inversions of the configuration. Inversions of the configuration. At first, tetrahedral ini, 3 kaki ini menghala belah kiri. So because of the backside attack by the nucleophile, then akan menyebabkan in the product the 3 bond itu inverted to belah kanan. Okay, that is what meant by inversions of the configuration. So for SN2 reaction, so the order of the reactivity decrease dari methyl halide pergi tertiary haloalkane. So kenapa decrease like this? Okay, it is because in SN2 reactions mechanism, okay, so the reactivity is determined by the steric hindrance. So the reactivity of haloalkane towards SN2 is determined by steric hindrance or steric effect. So apa maksud steric hindrance? So steric effect or steric hindrance basically refer to, so how crowded is the group around here. So if methyl halide or a hydrogen, So means that they are very small. So all these hydrogen are very small. So means that nucleophile in it easy to attack this carbon. Okay. However, if it is tertiary haloalkane, so tertiary haloalkane, for example, so tertiary haloalkane, these are all alkyl group. So this alkyl group ikat kepada hydrogen again. Right. Can you see that now? Sekarang, it is not easy for the nucleophile untuk jumpa this carbon. Not easy. Why? Because now, can you see that around here in the tertiary haloalkane, it is very crowded, very crowded. So they can block, so the group here, they can block the nucleophile from attacking this carbon. Because of that, the tertiary haloalkane is the least reactive towards SN2. Okay, so this effect is what we call as steric effect. Okay, is what we call as steric effect. So when you have more number of alkyl group bonded to the carbon that is bonded to the halogen, then apabila lebih banyak alkyl group, that means that bulkier. So it will hinder or block the nucleophile from attacking the carbon that is bonded to halogen. Therefore, slower is the reaction. Okay, so in methyl halide, semua adalah hydrogen. So nucleophile senang attack this carbon. But in primary haloalkane, ada satu alkyl group. So sudah susah untuk nucleophile attack this carbon. In the secondary haloalkane, there are two alkyl group. So these two alkyl group are big. So nucleophile makin susah nak attack this carbon. And in the tertiary haloalkane, there are three alkyl group. So even harder for the nucleophile to attack the carbon. Okay, that's why the reactivity towards SN2 decrease from methyl halide to tertiary haloalkane. So in SN2, must remember steric effect is important. So steric effect will affect the reactivity of the haloalkane towards SN2 reaction. Okay, when the carbon of the halogen bonded to the halogen, when it is being bonded to alkyl group, large alkyl group, the alkyl group that is very large, like for example, like this. Okay, so very large. Okay, so when very large, then this alkyl group can block the nucleophile from attacking the carbon. Okay, so therefore, the reactivity for this haloalkane towards SN2 will largely be decreased. Okay, due to the bulkier group ini menyebabkan steric effect tinggi, so harder for the nucleophile to attack the carbon that is attached to the halogen. So now we move on to look at how to write the mechanism for the SN2 reaction. Okay, so again, how to know whether that particular haloalkane will proceed through SN1 or SN2? So for SN2, first we need to determine the class of the haloalkane first. Like for example, for this haloalkane, it is attached to two hydrogen, so bermaksud satu alkyl group. So this is primary haloalkane. And this primary haloalkane, can you see that? So can you see that this primary haloalkane, so it is not having a lot of steric effect. Okay, so the steric effect is very low. So if steric effect is very low, then it is going to proceed through SN2 reactions mechanism. So for SN2 reactions mechanism, remember 2 means that at the slower step, it involves haloalkane and also the nucleophile. So the nucleophile here is hydroxide ion. So means that in SN2, we need to draw both at the first step. Okay, so the first step, we need to draw both. And for the SN2 reactions mechanism, the haloalkane, when we need to draw it in the tetrahedral shape. Okay, so how to draw it in the 3D tetrahedral shape? So first, we draw the carbon that is bonded to the halogen first. So this is the carbon that is bonded to the halogen. And then we draw the 3D structure, the bond, 3D bond. So how to draw the 3D bond? Just like how you draw the enantiomers. Remember, the dash and also the solid wedge, they must be on the same side. Another side is this. So this carbon is bonded to Br. So already draw the Br. And then bonded to 2 hydrogen. So hydrogen. And bonded to CH3. So CH3 like this. So done drawing the haloalkane. And then this haloalkane will be attacked by the nucleophile hydroxide ion from the back, opposite to the halogen. So if halogen you draw to the right, the electrophile you must attack from the left. Okay, so for hydroxide, the negative charge is on the oxygen. Therefore, you need to draw the negative charge on the oxygen. So attack the carbon, okay, that is holding the halogen, and then bond between the carbon and the halogen break. So this is the rate determining step, the slower step. So this step is slow. Okay, so this is rate determining step. So means that this step is slow. So after the nucleophile attack the carbon, okay, what will happen is we form the transition state. So how to form the transition state? Remember, the carbon partially form bond with the nucleophile. The bond between the carbon and halogen partially broken. Okay, so you need to draw it in the trigonal bipyramidal shape. So middle here, so CH3, and then remember trigonal bipyramidal. So HH, so this is transition state. So if you don't put the single double dagger, you can write this is transition state. And this is the activated complex that you get. And the charge is -1 because ini -1, ini kosong. So the total charge is -1. Okay, and then you form the product. So this is fast. So how to form the product? Again, remember the carbon, the tetrahedral become inverted. So on the reactant, you draw these 3 bonds to the left. In the product, because the configuration be inverted, you need to draw it to the right, pointing to the right. So pointing to the right. Okay, and here is your nucleophile OH. The carbon is bonded to the oxygen. Okay, it's bonded to the oxygen. So, and here is your CH3. Okay, and then the bromine will come out as Br minus, Br minus. Okay, so Br minus. So basically, this is your SN2 reactions mechanism. Okay, SN2 reaction mechanism. So just now we have seen, we already discussed for tertiary haloalkane, definitely will undergo through the nucleophilic substitutions reaction through SN1. For methyl halide, definitely SN2 because the steric effect is the lowest. How about primary? So must be careful for primary haloalkane, not all the time undergo SN2. Okay, not all the time undergo SN2. Like for example, this compound here, this compound is 1-bromo-2,2-dimethylpropane. It does not undergo SN2. Why it does not undergo SN2? It is because of this bulky alkyl group that block the carbon, this carbon, from being attacked by the nucleophile. Okay, so because of that, this primary alkyl halide do not undergo SN2 because of the presence of the bulky alkyl group that actually made the nucleophile very difficult to make the bedside attack. Okay, very difficult to attack the carbon that bonded to the halogen. So this carbon. So this big alkyl group block nucleophile from attacking this carbon. Okay, and this effect is what we call as steric effect or steric hindrance. Okay, so because of that, due to high steric hindrance, so this primary haloalkane actually proceed through SN1 reactions mechanism by undergoing rearrangement to form more stable carbocation ion. So shall we have a look on the reactions mechanism? So again, this is primary haloalkane because it is having 2 hydrogen, so means that 1 alkyl group. So this is primary haloalkane. But this primary haloalkane, so high steric hindrance or high steric effect. So high steric effect, so won't proceed through SN2. So SN2, no, because high steric effect due to large alkyl group. Okay, so it will proceed through SN1 through rearrangement to form stable carbocation ion, tertiary carbocation ion. So we will look at this, how it can form more stable tertiary carbocation ion. Okay, so remember for SN1, so step number 1 is formations of carbocation ion. Okay, so how to form the carbocation ion? Remember, this is SN1, means that step number 1 only involve the haloalkane. So step number 1 only involve haloalkane, so you only draw the haloalkane. So only draw the haloalkane. Again, so remember how to form the carbocation ion? It is through carbon halogen bond. So this bond break. So when the bond break, both electron will go to bromine because it is more electronegative. But when this bond break, you will get primary carbocation ion. that is not stable. So what will happen is 1,2 hydride shift. Okay, again, what will happen? 1,2 hydride shift. So you will get more stable tertiary carboxyl ion. Okay, so this is again, this step is slow, so therefore it is the rate determining step. And then this step basically involves 1,2 methyl shift in order to get more stable tertiary carboxyl ion. Number 1. Then in step number 2, remember nucleophilic attack on carboxyl ion. So after step number 1, you get your stable tertiary carboxyl ion. Right. Okay, so you get your stable tertiary carboxyl ion, and then this carboxyl ion will be attacked by your nucleophile. So the nucleophile is this one. So this is the nucleophile. Okay, the alcohol. So CH3H. So rich in electron. At where? At the oxygen. It has 2 lone pair. Okay, so the alcohol will attack the carbon that is carry the positive charge using the lone pair on the oxygen. So you get CH3, CH3, CH2, CH3. So one lone pair, so forming one bond. Can you see 1, 2, 3, 4, 5? So 6 valence electron minus 5, so you get positive 1. Okay, so that is step number 2. So step number 3, you want to, okay, so loss of proton. So you want to remove the hydrogen. Okay, so basically here, you can either remove hydrogen or methyl. Remember, which one easier to remove? Hydrogen, because smaller. Therefore, hydrogen will be removed. So to remove hydrogen means that the bond between the oxygen and the hydrogen must break. So this bond must break. So it will break heterolytically. So both electrons will be taken by the oxygen because oxygen more electronegative. Okay, and then someone need to remove the hydrogen. So who will remove the hydrogen? Will be the nucleophile. Will be the nucleophile. So CH3 O H. Okay, so the nucleophile will use the lone pair to get the hydrogen. So you get your product CH3, CH3, CH2, CH3, so OCH3. So this is the product, the major product. Okay, so this is how we do this question. So now we move on to look at how about, so what can we summarize is if primary haloalkane can undergo SN1 or SN2, but if high steric effect cannot SN2, it need to proceed through SN1 by having rearrangement to form more stable carboxyl ion. Okay, it will proceed through SN1 involving rearrangement to form stable carboxyl ion. That is for primary haloalkane. How about secondary haloalkane? For secondary haloalkane, we need to look at nucleophile. For secondary haloalkane, we look at the nucleophile. For strong nucleophile, so strong nucleophiles such as, again, cyanide ion, hydroxide, and also alkoxide. So these are strong nucleophile. So secondary haloalkane with strong nucleophile, it will proceed through SN2. If with weak nucleophile, such as water or alcohol or ammonia, then it will proceed through SN1. Okay, so secondary haloalkane, we look at the nucleophile. Okay, so now, shall we do this question? So determine whether a substitution will take place by SN1 or SN2. So this is the haloalkane that is been given to us. So again, first we need to determine what is the class of the haloalkane. So this haloalkane, so to class it, so circle the reference carbon. It has one hydrogen. So if one hydrogen means that two alkyl group, so two alkyl group, secondary haloalkane. So if secondary haloalkane, it is determined by nucleophile. It is determined by the strength of the nucleophile. Okay, so the strength of the nucleophile. So hydroxide is strong nucleophile. So if strong nucleophile with secondary haloalkane, then the reaction, the nucleophilic substitutions reaction, will proceed through SN2 reaction mechanism. So if water is weak nucleophile. So if weak nucleophile, then the secondary haloalkane will proceed through SN1 reactions mechanism. So now, shall we move on to look at PSPN 2009 question? So 2-bromobutane react with KCN to give 2-cyanobutane. So butane, 4 carbon, 2 bromo. So this is CH3, CH2, CH, CH3. React with KCN, giving us 2-cyanobutane. So can you see that Br is being substituted by Cn? So if Br being substituted by Cn, so the type of reaction is definitely substitution. Remember, this is organic chemistry. We need to look at the carbon where the reactions occur. It is partially positive charge, so it is being attacked by the nucleophile. It is being attacked by the nucleophile, therefore this reaction is nucleophilic substitutions reaction. So state the type of state the nucleophile in this reaction. So again, I told you already, KCN, this is ionic compound. So in ionic compound, you have the cation and also the anion. So which one is the nucleophile? Nucleophile rich in electron, so it will be the cyanide ion. So it's the cyanide ion. It's the nucleophile. So ask you to write the chemical equation for the above reaction. So I have written the chemical equation. So the byproduct is KBr. Okay, so this is the chemical equation. And ask you to draw the 3D structure of 2-cyanobutane. Okay, so 3D structure. So for this one, I want to change a bit. Shall we draw the mechanism? So for this reaction, draw the mechanism for the reaction. So want to draw the mechanism, you need to determine is SN1 or SN2. So shall we have a look? So to know whether it's SN1 or SN2, first we need to look at our haloalkane. So look at this haloalkane. Circle the reference carbon, ada satu hydrogen. So kalau satu hydrogen bermaksud dua alkyl group. So this is secondary haloalkane. So remember, secondary haloalkane, to know the mechanism, we need to look at the nucleophile. So nucleophile is CN minus ion. So cyanide ion. This cyanide ion is strong nucleophile. So if strong nucleophile means that this nucleophilic substitutions reaction, okay, of haloalkane is proceed through SN2 reactions mechanism. So if SN2, how should we draw the reactions mechanism? Again, the haloalkane 2 bermaksud we need to have the nucleophile and also the haloalkane together. So how to draw the haloalkane? We need to draw in the 3D. So this is Br. So and then in 3D, so draw the bond first. Okay, so attached to hydrogen, attached to the methyl group CH3, and another one is CH2, CH3. So this is your haloalkane. So react with the nucleophile. Remember SN2, you kena lukis kedua-dua, your haloalkane and also your nucleophile. Again, I told you already in the cyanide ion, the negative charge is on the carbon, Okay, so when react is the negative charge on the carbon will attack the carbon that carry the halogen. So bond forming, bond breaking. So this is the slow step. So therefore, this is the rate determining step. Okay, so the rate determining step. So then giving us the transition state. So transition state. So the nucleophile partially form bond with the carbon. So it's the carbon of the cyanide ion that is attached to the carbon. And with the halogen, bond partially break. Okay, and need 5 bond. So you need to draw, remember, trigonal bipyramidal shape. So the H, CH3. So you either draw the double dagger sign or you can write this is transition state. And the charge is negative because negative 1 kosong, so negative 1. Okay. And here very fast the carbon halogen bond break. Okay, and then the tetrahedral will be inverted. Okay, the carbon tetrahedral will be inverted. Yani point to the left, so lepas inverted will be pointing to the right. So pointing to the right. So CH3, and this is CH2, CH3, and here is your CN. And the bromine will leave as bromide ion. Okay, so this is how you draw the SN2 reaction mechanism. So this exercise 1, okay, so determine whether substitutions reactions will take place by SN1 or SN2. So for this question, again, first we determine our haloalkane. So this haloalkane, so here is the carbon that bonded to halogen. So this carbon has one hydrogen, right? So has one hydrogen. So means that two alkyl group. So this is secondary haloalkane. So if secondary haloalkane, we need to look at the nucleophile. So we need to look at the nucleophile. This nucleophile is weak nucleophile. So this is weak nucleophile. So if weak nucleophile, it will proceed through SN1. Okay, it will proceed through SN1. Okay, so again, if proceed through SN1, so before we move on to look at the mechanism, so shall we draw the product? So remember, this nucleophile kaya dekat nitrogen will go in, attack the carbon that is carry the positive charge, partially positive charge, and then tendang keluar Br. So you get this. So tendang keluar Br keluar will take one of the hydrogen. So you get NH2, CH3. Remember, this is SN1. So SN1. So remember, SN1 punya intermediate is carbocation. So when Br keluar, you get secondary carbocation. So possible for it to rearrange to get more stable carbocation? Yes. Yes. So means that you will have another product. Which is this. Okay, and this is the major product because it is formed from more stable carbocation. So shall we look at the mechanism? Okay, so shall we look at the mechanism? So we already know it is SN1. So if SN1, 1 means that at the step number 1, formations of carbocation only involve one species, which is the haloalkane. So bermaksud kita hanya perlu draw the haloalkane in step number 1. So how to get the carbocation? So basically, this bond will break. Okay, so you get the secondary carbocation. So this step is slow, and therefore it is the rate determining step. And look at the carbon here. This is the carbon next to the one carry the positive charge. This carbon is tertiary carbon. Okay, so tertiary carbon, so means that rearrangement possible to occur. So again, it will move the hydrogen instead of methyl because lebih kecil. So move here. Then we get, so the hydrogen is here now. We get tertiary carbocation, which is more stable. That's why you get two products. So this product is from secondary carbocation. Okay, so which is less stable, that's why it will be the minor product. And this product, major product, is from the tertiary carbocation. Okay, so we draw the mechanism for major product. So step number 2, nucleophilic attack on carbocation. So just now, step number 1, we get our carbocation. Our nucleophile is ammonia. So ammonia is rich at the nitrogen, has one lone pair. Go attack the carbon that carry the positive charge. So giving you CH3 and H3. So here will be positive. Why positive? So again, nitrogen 5 valence electron. So here 4 bond. So 3 plus 1, 4. So 5 minus 4, positive 1. Okay. Then in step number 3, loss of proton. So we want to get a neutral product. So basically, you get NH2. So the nitrogen and the hydrogen bond must break. So break, go to nitrogen. Someone must take the hydrogen. So who will come in to take? So you only have ammonia. So the ammonia will come in to take the hydrogen. So you get your product, the major product. So 4 bond, positive charge. Okay, so we quickly do exercise number 2. So arrange the following haloalkane in increasing order of SN2. So hydrolysis reactions with sodium hydroxide. So again, SN2 reactivity is determined by steric effect. So remember, larger steric effect, lower reactivity. Towards SN2. So now shall we look at this? So this haloalkane, so again, this carbon has 2 hydrogen, so means that it is primary haloalkane. 1 alkyl group. So this carbon, 2 hydrogen as well, so 1 alkyl group. one alkyl group, so also primary haloalkane. Look at this carbon, 2 hydrogen, 1 alkyl group, also primary haloalkane. Oh, primary haloalkane, how to determine? So maybe we can draw out the structure, then we can determine. So this carbon, CH2Br, and then attached to CH, so CH3 and CH3. Okay, so for this one should be no problem. It is a straight chain, so it is a straight chain. So just CH3, CH2, CH2, CH2Br. So it's a straight chain like this. How about this one, the last one? So the CH2Br, so C, CH3, CH3, CH3. Okay, all are primary haloalkane. But which one has higher steric effect? So larger steric effect lowers the reactivity. So which one has the largest steric effect? So remember, steric effect is determined by how bulkier. So bulkier, larger or bulkier alkyl group. So means that lebih banyak substituent. So can you see that? Oops, 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 oops. Okay. Okay, so can you see that for this one, this is the alkyl group. Okay, so only have one substituent. This one, straight chain. This one, 2 branch or 2 substituent. So which one bulkier? So this one is the bulkiest. Okay, so this one is the bulkiest. So means that this one has the largest steric effect. So this one bulkiest, so largest steric effect. So bulkiest, so largest steric effect. So the least reactive towards SN2. Okay, so followed by this. So this one is slightly less bulkier. So the steric effect is slightly lower. So the reactivity towards SN2 is higher compared to the, so I put 1, 2, 3. So the first one, okay, the reactivity is slightly higher than the third one. Okay, and this one is the smallest, okay, alkyl group. So the least steric effect, so is the most reactive towards SN2. So ask you to arrange in the increasing order. So it will be number 3, okay, followed by number 2, number 1, followed by number 2. Okay, so increase reactivity towards SN2. Okay, so how to explain? So your point number 1, you must say SN2 reactivity is determined by steric effect. Okay, it's determined by steric effect, and you must say larger or bulkier the alkyl group, larger steric effect, lower reactivity towards SN2. Okay, and then you can say Number 3, bulkiest alkyl group, largest steric effect, so least reactive towards SN2. Okay, and then you can say number 2, the smallest alkyl group, so lower steric effect, so the most reactive towards SN2. Okay, so this is also popular kind of questions. So do need to take notes of this. Okay, so that's it for tonight. So thank you, class. So you can scan your attendance and then fill in the Google form. Okay, so to record your attendance. Okay, so in the Google form, so I ask you 2 questions. So hopefully you can get them right. So, and the homework. So for 172, so 172, I have finished the whole haloalkane chapter. So you can do the haloalkane question number 1 until question number 13. So for 146, 332, and 234, you can do question number 1 until question number 9. Okay, so other classes I will continue tomorrow to finish this chapter. Okay, so good night, everyone. Do say good night to madam. Okay, then I will see you tomorrow. Bye bye.